Hi there, and welcome to the second tutorial in the series I'm now calling Python Millionaire Retirement Simulator. Was that a great title or not? Probably not. So, last time we kind of set up the bones of our simulation, and we were taking this empirical approach. The way that we actually save money for retirement is kind of every paycheck we put a little bit of money away and something magic happens. Well, now we're going to start to get into creating the magic. And so just to review here, we imported a few things, sys, and then a few things from date time. We took today's date. We took a few epochs of time. We created a pay frequency, which we said was 2 weeks. We had an amount already in retirement. We determined our number of paychecks per year by taking 1 year and dividing it by our pay frequency. And then we also changed it from having, putting a fixed amount in to a different fixed amount that's based on a salary. So we had a salary, and we figured out what one paycheck was, dividing the current salary by the number of paychecks you get a year. And we said we are adding 10% to our retirement. We picked a retirement date. And so then we defined our retirement as being the amount we already have in retirement. And then we stuck this while loop into action where we said as long as today's date is less than the retirement date, then we want to add money to our retirement. We take our retirement and we say plus equals. That means take our retirement and add this to it, but save it as retirement. So retirement equals retirement plus the add to retirement portion. And then we did the same for the today's date. We had today's date and we added the pay frequency to it so that the date incremented by 2 weeks in our case until the date was greater than the retirement date, at which point we broke out of the loop and we printed, I have so much in my retirement as of today's date, which was now the new date. Then we did a test at the end, and in the test we just set our retirement to $100. We added $1 to it and looped over the number of paychecks per year, which was 26. And when we did that, we saw that we have this output right here where we added $1 each time, just as expected, 26 times. And so that was just a verification, a confirmation that our code does the thing we think we. I know that I was using a for loop instead of a while loop, but I hope you'll indulge me in your belief that the principle is the same. All right. Having reestablished everything we did in our first tutorial, now we're going to take this test and we're going to comment it out. In my version of Spider, I've learned that you can do what I just did. You can select a portion and comment or uncomment it by using Control+1. So Control+1 takes the comment away, and Control+1 puts the comment back. Okay, so we're going to comment that out to start. And then really the only nuance that we're going to do is we're going to add an annual interest rate. Well, okay, I say the only nuance. We're actually going to do a little bit more nuance than that. And the reason is this. When you can look up data for what kind of interest rates the market, returns, there's a distribution. And it follows what you'd call a Gaussian shape. It's kind of a bell curve. And this distribution of dates is for the annual interest rate, meaning if you put in, $100 on January 1st and the market, you had a 5% yield for the year, then at the end of the year, your $100 investment now was worth $105, okay? But that's not what you do, right? When you put money away for retirement, you put money away every day, and then every day it earns some incremental small amount of interest so that at the end of the year, that money you put away on January 1st would have earned, if it was $100, it would have earned $5. But the money you put away on, December 1st doesn't earn as much. And of course, not only that, but you're putting the money away incrementally along the way. So what we need to find out is a kind of a fractional interest, and there's some math involved. And hopefully you'll trust me because I've done the research and figured out the math, and the math should all check out. But basically, it's going to be that the annual interest rate, you want the annual interest rate such that if you had a different number that was what you would call, in this case, maybe a biweekly interest rate or some fractional interest rate, that if you raised it to a power that was equal to 1 plus the interest rate times to the power of the number of paychecks you get a year, that should equal the annual interest rate. Okay, and that's really esoteric, but here, I'm going to just copy this comment and put it in here for the sake of, and hopefully this comment should be available once everything is on the website. You should be able to see this down in the notes below. But this is the comment. We want to convert the annual interest rate into a biweekly interest rate, and we're going to actually be a little bit even more more general than that. So first, let's just define an annual interest rate. And can I spell annual right? Yeah. Annual interest rate equals 0.05. So we're just going to start off with a guess of 5% for an annual interest rate. So that would be a pretty good return, right? You put your money away, it earns 5%. Great. We want to turn that into what I'm calling a biweekly interest rate. And so the biweekly interest rate should be such that 1 plus the biweekly interest rate to the power of 26, since that's the number of paychecks we get a year, equals the annual interest rate. And so here's the math. You take the log of both sides, which gives you 26 times the log of 1 plus the biweekly interest rate equals the log of 1 plus the annual interest rate. And you can move the 26 over to this side, and you can now take the exponent of each side. And so you add 1, or I'm sorry, you subtract 1 now from this side, and you end up with the thing you want, the biweekly interest rate equals this funny expression where there's an exponent, 1 over 26 times log of 1 plus the annual interest rate, and then minus 1 at the end. Okay? So we're going to make a definition now. And the definition we make is going to determine what we call a paycheck interest rate. Okay? So def get underscore paycheck. I can't type. Interest underscore rate. And we need to take as input for this definition the annual interest rate. Annual interest rate, comma, and the number of paychecks, so the paychecks per year. And we do have that as a suggestion here. Okay, so that's our input. We need to put a colon after our definition, and now we should be tabbed out, which we are, where we have a 4 space between the start of our definition and the next line. And so all we need to do is return this final expression here, this exp 1 over 26. But 26 is going to be the paychecks per year number. And so, and to do this, we're going to use the NumPy package. So let's go up to the top of our file. And it's struggling a little bit here. Okay, here we are. And we'll say import NumPy as np, which is a standard way to import the NumPy numbers.py package. Okay, and the np just means when we want to use it, we invoke the letters np. So we're going to, in our definition back now with the spaces, we say return, because we only need this one line, np dot exp, meaning take an exponential. So we're just going to follow, and I'm getting tired of all these suggested comments. They're super annoying. But we're going to copy this expression here. And so double parenthesis. And what do we want to say? 1 over paychecks per year. So we'll copy that. 1 over paychecks per year. And then outside the first set of parentheses, then we'll say times np dot log, open close parentheses, And inside the parentheses for the open close log, we'll say 1 plus, and we'll copy this, annual interest rate. And then we need to, I think that outside of the, let me just double check this here. Yeah, so outside of the exponent, we're going to subtract 1. And that's what we want to return. And so I'm going to just show you from this other text a little bit cleaner looking here. But it's the same thing. It's numpy.exp 1 over number of paychecks per year times np log 1 plus annual interest rate minus 1. This one was called number of paychecks per year rather than paychecks per year. But I digress. Okay, so this is what we return from our get paycheck interest rate definition. And so now we want to use our definition. So outside of the var while loop, we will say, in fact, we can just copy this whole thing, and we'll say paycheck underscore interest rate equals get paycheck interest rate, and we use the annual interest rate, which hopefully is the same, yeah. And the paychecks per year is the same. Okay, I'm highlighting it here to make sure that the number I'm using down here is the same spelling and everything. Okay, so now we have a paycheck interest rate, and so we're going to use that in our retirement. So now, after we've added money to the retirement account, we're going to say a very similar expression, retirement, and now instead of plus equals, we're going to say times equals. So that would be star equals, and now we want to use the paycheck interest rate. Okay, so and let me just make sure that that's, in fact, just to be clear, we actually want to say 1 plus the paycheck interest rate. Because multiplying by 1 would do nothing. And any number times 1 is the same number. So we want to do 1 plus the paycheck interest rate, which again, it's some fraction. We subtracted 1. We could have not subtracted 1 and left it, but anyway, for me, this was a clearer thing to say because this number should be less than our annual interest rate, and it is. And we're going to do a verification at the end of this tutorial to verify that, in fact. Okay, so if we remember from the last time, maybe it's on here, we had $51,383.46 as of the date. So now, if we start putting our money away and it starts earning this fractional interest rate, and that's the only thing that we've really changed is to the while loop, we'd like to see now what happens. So I'm going to hit, I saved it, and I'll hit play, and hopefully we don't have any errors. All right, so now we have $66,265. So you see that we had 51, now we have 6. We've earned $15,000 of just interest, just from a standard 5% interest rate. Now, you know, most things don't give you a safe 5% interest rate these days, as far as I know. But still, you know, that just shows that we're doing better than just putting money under our mattress. And so we have a different test today. And again, I'm going to copy and paste it and then go through it with you. But it's the same idea, where we have our retirement. We're going to start with $100. We're going to print the word test so we can tell that it's the test. And then we're going to loop through the number of paychecks per year. And what we're going to do is, instead of adding anything to our retirement, we're just going to take our number. And again, we're going to do that scenario where we had $100 on January 1st. And then we're going to just add the interest. And so the interest in this case is the paycheck interest rate, right? But if we add it 26 times throughout the year, and we look at the end result here, then we're hoping that the end result should be $105. And so we're going to look at the interest as the year moves on, but the last number should be $105. So I think everything looks in order there, and we're just printing. We're using the NumPy round feature for the retirement. We're putting it 2 decimal places in case that wasn't obvious. Okay, well, let's save it and run it. Oh, number of paychecks per year, right? That's the problem with copy and paste. Okay, it's just paychecks per year. There we go. So save and run. And boom. Okay. So again, we started out with 100. Our first paycheck, we got 19 cents, 38 cents, 56 cents, 75 cents. So this is our account accruing interest slowly over the year. And we finally get up to $1, $1.70, $2, $3, $4, and we ended the year with exactly $105. And so hopefully, again, that verifies to you that the math we did is the correct math. And we can even do a further verification where I can change this interest rate to 10%, and I save. And now the interest should change so that we have $10 at the end of our paychecks. Yep, $110. And then finally, just to be even more clever, I can change our pay frequency so that instead of getting paid every 2 weeks, maybe we get paid twice a month. So I can say semi_monthly equals 1 month over 2. And then I change my pay frequency instead of every 2 weeks to semi-monthly. So this would be 24 paychecks instead of 26. And if that, hopefully that doesn't change our final, we should still get the number 10 down there at the bottom. And I'll look up here. So in this case, if we were earning 10% a year, we'd end up with $85,000 in our account and 66 cents. So this may change the last day. So now we're ending on 4/02 rather than because we started, today's a different day than yesterday. But that's fine. Okay. I'm babbling here, but let me run this again. Did it work? I just want to verify. Okay, it did work. So we still ended up with an extra $10 for our test. 86,981 versus, just to be sure, 85,529, and we ended on a later date of 4/08 because we were getting paid semi-monthly based on getting paid today and then every basically 15 days or so after that. So a slightly different result there for the money because we're getting paid on a different frequency, and so the paycheck interest rate might be slightly different, but obviously we can see that for $100 that sits in there all year, no matter what our pay frequency is, we're still ending up with $110. So that gives us confidence that the math we did there is correct. Well, thank you for watching and hanging in there this long. And the next time you watch, we are going to add a few more features where I think next time we're going to invoke that Gaussian distribution. So instead of having one interest rate, we're going to maybe sample and we'll put in some triggers so that every year we get a new interest rate that's in some Gaussian distribution. And that's just our Gaussian distribution will be our guess as to maybe a realistic distribution, and then from there we'll move on to getting an actual realistic historical data distribution from which to draw. So if you stick around, we'll keep doing that. And then once we add in this feature where we can change the interest rate every year, we can also do things like change our paycheck. So you maybe you make whatever you make now, but perhaps you get a raise every year, and so you could change your current salary. And then if you're doing 10% of your paycheck to retirement, that's also going to change. So you can incrementally change how much money goes into retirement in a realistic way, while you're also incrementally changing your interest rates in a realistic way. And so we can add more and more realism to the simulation as we go. So thank you for watching. Thanks for sticking in there. Python Millionaire Retirement Simulator. I hope you enjoyed it, and I'll see you in the next one.